So you are welcome back, students. So we want to now look at definite integral. Definite integral is basically the area under the curve between a closed interval. So we are looking for the area under the curve. It's not like the indefinite where it's actually from infinity to infinity, negative infinity to positive infinity. But this time around, we want to determine the area, specific area. That's why it's called definite of the under the curve between a closed interval. And normally when it comes to definite integral, you get a value for it, unlike indefinite where you get a function. So I want to quickly look at that quickly. Now I will set up some few sample functions, then we will find the definite integral. I will look at this simple cubic function, f of x equal 2x cubed plus 7x raised to the power 2 minus 5x and then plus 3. Let me change it. Minus 3. So I have this function, a cubic function here. So this is a cubic function. So I would like to zoom a little bit so that I can get the cubic function. Well, so that's a cubic function. Okay. So that's a cubic function that you are seeing. Now I want to find the definite integral. Now, to find a definite integral, one of the things that helps in determining that is the idea of what's called a Riemann sum. As I mentioned to you earlier on, that when it comes to integration, integration is about the sum. So you're looking for the Riemann sum, you're looking for the sum, the area under the curve. In this case, within this specific interval. So we have to first identify an interval, then we will find the area under the curve within that interval, which is called the Riemann sum. So what I'm going to do is I will just pick up an interval, and so I'll use some points. So I will look for 2 points. I'll look for 2 points. So let's say I have this point here, this point A here, and then I have another point B. I have another point B. So I have these 2 points. Now I want to find the area under the curve between these 2 points. These 2 points now yield an interval, a closed interval to be specific. So we're going to use the x coordinates for the A and the B respectively to now find the area under the curve. But when, as I said, we're going to use the Riemann sum. And the Riemann sum is basically, we have the upper sum, which is the area of the upper section of the area in question, and we have the lower sum. So we're going to do that. But before then, we need to know how many triangle divisions are you going to have. So how many rectangle divisions are we going to have? So for that, I'm going to set up a slider, and then I will name the slider to be n, and I'll make it to be an integer, positive integer. And then you start from 1, and I'll let it to end at somewhere 150 and an increment of 1. So that's the slider. Okay, so we would now look at how to determine the upper sum. So we would find the upper sum. Now I will just want to acronym the upper sum to be UPS. And so upper sum is equal to, then equal to the upper sum. Then we have the function is f, and then the start. I'm looking at starting from A to B on the x-axis. So I'm saying that my x is going to be my start is going to be the x coordinate for the A, and then my end value is going to be the x coordinate for B. And then the number of rectangles I'm going to set up to the slider. Okay. So we have this as our upper sum. And then GeoGebra has done our calculation for us. The upper sum, when n is equal to 1, in other words, we have just one rectangle, and our upper sum is equal to 80.48. So that's the upper sum. Okay. Now I would like to do some coloring just for us to be able to see the difference between the upper sum and the lower sum. So I will use this color. Okay. And this will be my upper sum. All right. So you could see as I increase the n, it divides the upper sum into several number of what? Rectangles. And then the area for the upper sum increases as the number of rectangle also increases. So that's what is used for the approximation for the area under the curve within this particular interval, which is supposed to be a closed interval. That means that the point x along the A and then the B coordinates are all inclusive. Then we'll look at the lower sum. Lower sum, I'll just use the acronym LPS equal to, then lower sum. And lower sum 2 is going to be the same. And the function is f. And my start is going to be the x. I'm going to use the x coordinate of the A. And then I'll use the x coordinate of the B as well. Okay. Then number of rectangles, I will use the slider so I can determine the slider. So that's the lower sum. Now the lower sum is set to 0 at n is equal to 1. That means that it's set to 0. So the lower sum set to 0. So what I'm going to do is that I'm going to also shade the lower sum. So I'll color the lower sum. I'll use this lemon green for the lower sum. Okay. Oh, I use the lemon green for the upper sum. I can't use I have to change it. So I'll use, this is interesting. So this is the lower sum. And so we have the lower sum. So you can see that when n is equal to 1, the upper sum is 80.48. When n is equal to 1, lower sum is 0. Now what I want to create a dynamic text so that we can keep these things much more visible. So UPS value. Okay. And then I'll create another one. LPS value. And then I'll create this also. So these are the values. So we want to see that. Okay. Then so we are done with this. So we found the lower and then the upper sum. So now an observation that you have to make. And so I will set the animation on before we find the integral. So just observe the upper sum and the lower sum. You see that as the n increases, the upper sum and lower sum are getting closer and closer to each other. So you can see that they are getting closer and closer to each other. 51, 49, 50, 49, 50, 49. Very, very close. Now, if I increase my maximum to 200, you see what is going to happen now? And put animation on. You see that it will just be getting closer and closer. They will just be getting closer and closer to themselves. So what we are saying that the upper and the lower sum, they are very, very good approximation of the indefinite integral. Okay. Now let's now find the indefinite integral itself. So I say indefinite, the definite integral, sorry. So that one is going to start from we have the third one, we have the function f of x, and then the start value is going to be x as usual, and then the a. Then for this as well, the x, and then the b, the point B, the x coordinate of the point B. So we have this. So that will give a definite integral. So definite integral is 50. So all right, so it's 50. Let me see if I can create a text for it. Let me see if I can create a text for it. Okay, so I'm able to create a text for it. Okay, so let me color each of them. The upper sum is lemon green, and then lower sum is red. Just want to color it just to differentiate. And then our text is this color. Good. So we have this. So now when we will start the animation for us to be able to see it and look at the upper sum, both the upper sum and lower sum. As the number of rectangles increases, you can see that it gives us some very, very close and correct approximation of our definite integral. So that's basically what I wanted to demonstrate. So as the limit of n increases, okay, then what happens is that our Riemann sum will be equal to the definite integral. So that's how we're able to approximate a definite integral. It's very, very important. Okay, so that is it. So we would take another example. Maybe this is okay. I think this is okay. Just demonstrating the approximation of the definite integral. We've looked at that of the indefinite integral as well. So on that note, we will just close the chapter 2, integration of polynomials. I hope that you've learned so much, students. Let's meet in the next class. Thank you so much.